Okay, we're going to carry on still with the chapter on field effect transistor amplifiers and switching circuits, specifically section 9.3, the common gate amplifier, the last of the three configurations of field effect transistor amplifiers. Alright, let's have a look at the introductory paragraph in our textbooks on page 451. The common gate amplifier. The common gate field effect transistor amplifier configuration is comparable to the common base BJT amplifier. Can you imagine? Like the common base, the common gate amplifier has a low input resistance. This is different from the common source and the common drain configurations, which have very high input resistances, if you can recall. Anyway, I have to be able to recognize the configuration of amplifier, of course. And here I can see a common gate amplifier. Where is the input? And where is the output? And I can see the gate is connected to ground. So that is the configuration of amplifier. Alright, let's have a look what's going on in the textbook. It says there, a self-biased common gate amplifier. Obviously you've seen that it's a self-biased method of biasing that's been used. Connected directly to ground, as we've seen. The input signal is applied to the source terminal through C1, and the output is coupled through C2 from the drain terminal, as we've seen. Alright, the voltage gain in this case as we've seen, always output voltage divided by the input voltage. For this specific configuration of amplifier is VD over VGS. Replace ID RD over VGS. Replace GM VGS RD over VGS. VGS cancels out, so the voltage gain is GM divided by RD, where RD, of course, is a small letter d. If there is a load resistor, it is RD in parallel with RL. And also that I've marked there, they said, notice that the gain expression is the same for the common source JFET amplifier, if you can recall. Anyway, the input resistance. Again, as you have seen, both the common source and the common drain configurations have extremely high input resistances, because the gate is the input terminal. In contrast, the common gate configuration, where the source is the input terminal, has a low input resistance. Okay, so they show it here. First, the input current is equal to the drain current. Second, the input voltage is equal to VGS. Therefore, the input resistance at the source terminal, V in over I in, VGS, GM, VGS. So, R in at the source is 1 over GM. And they used an example here. GM has a value of 4,000 microsiemens. Then R in at the source is the reciprocal of that, of course, 250 ohms, which I can see is fairly low. Let's have a look at the example at the bottom of the page, example 910. Determine the minimum voltage gain and the input resistance of the amplifier in figure 923. VDD is negative because it's a P-channel device. You have to be able to notice that by now. Alright, again, it is not mentioned what configuration of amplifier this is. So you can see it's important that you recognize the configuration of amplifier so that you know which formulas to use. Anyway, let's have a look at the solution on page 543. From the data sheet in figure 921, GM is 2000 microsiemens minimum. Go and test yourself, see that you can find that value from the data sheet. Okay, you have to be able to find the value from the data sheet to be able to do the problems, of course. This common gate amplifier has a load resistor. If you can look on the previous page at the figure, there's a effective drain resistance is then RD in parallel with RL. Remember, you have to calculate that. So, voltage gain then GM, that resistance R small d, RD in parallel with RL, and the answer there, the voltage gain is then 10. Input resistance, as we've seen, is 1 over GM, 1 over the 2000 that I found on the data sheet, microsiemens, gives me a value of 500 ohms. Then the signal source actually sees RS in parallel with R in the source, so the total resistance is then R in source in parallel with RS, 500 in parallel with 400 ohms in this specific case. Alright, we're going to have a look at another type of amplifier, the cascode amplifier on page 453. Please mark as I have done. One application in which the common gate configuration is found is the cascode amplifier. Commonly used for RF radio frequency applications. A cascode amplifier is one in which a common source amplifier and a common gate amplifier are connected in a series arrangement. What do I have when I have amplifiers connected in a series arrangement? Multi-stage amplifiers, né? As we've discussed previously. What do I know about multi-stage amplifiers? Voltage gain. I have to find the voltage gain of each stage, because I'm going to multiply the two to get the overall voltage gain, né? Alright, so the input stage is a common source amplifier and its load is the common gate amplifier connected in the drain circuit, as we can see. The cascode amplifier using JFETs provides a very high input resistance, you can underline that, and significantly reduces capacitive effects to allow for operation at much higher frequencies. That's why we've seen used where? Radio frequency applications. Alright? Much higher frequencies than a common source amplifier alone. Internal capacitances, which exists in every type of transistor, become significant at higher frequencies and reduce the gain of inverting amplifiers, which we've seen basically in chapter 10, because we have discussed chapter 10 already. Né? So the first stage, common source amplifier that inverts the signal. However, the gain is very low because the low input resistance of the common base amplifier that it is driving. As a result, the effect of internal capacitances on the high frequency response is very small. The second stage is a common gate amplifier that does not invert the signal, so it can have high gain without degrading high frequency response. So the combination of the two amplifiers provides the best of both worlds, resulting in high gain, high input resistance, and an excellent high frequency response. Right. So the voltage gain of the cascode amplifier in figure 924 is a product of the gains, as we've seen with multi-stage amplifiers, of both the common source and the common gate amplifier. However, as mentioned, the gain is primarily provided by the common gate amplifier, as we can see here. Voltage gain is the voltage gain of the common source multiplied with the voltage gain of the common gate, which is GM common source RD GM common gate XL. Since RD of the common source amplifier stage is the input resistance of the common gate stage, and XL is the reactance of the inductor in the drain of the common gate stage, the voltage gain is, not going to read everything, finally GM of the common gate times XL. Ne? XL, reactance of the inductor, knowledge that you've gained in electrical engineering subject. Ne? Alright, so the voltage gain is that, assuming that the transconductance of both transistors are approximately the same. So from the equation you can see that the voltage gain increases with frequency because XL increases. Okay, you can see that from the from that formula. As the frequency continues to increase, eventually the capacitance effects become significant enough to begin reducing the gain. Alright, and then the input resistance is to the cascade amplifiers, the input resistance of the common stage amplifier. Of course, Rn is R3 in parallel with VGS over IGSS. Let's have a look quickly at that last example. Example 911. It's got nothing to do with the two towers. For the cascade amplifier in figure 924, the transistors are 2N5485s and have a minimum GFS of 3500 microsiemens. Also, IGSS is equal to minus 1 nanoamperes at VGS is equal to 20 volts. Then it says if R3 is 10 mega ohms and L is equal to 1 millihenry, determine the voltage gain and the input resistance at the frequency of 100 megahertz. So they basically gave you all the information to be able to use these formulas. So you just put all the values in there, AV, voltage gain, GM of the common gate XL, and GM common gate 2 pi FL, and I just put all the values in. In this case, 2199. It's actually quite strange that they wrote it in this American book like this. Normally it's 2,199 if they mean thousands, nah, if you can recall from the previous examples. Anyway, Rin is then R3 in parallel with VGS over IGSS, and you can see again previously that they've said it is equivalent to the value of R3. Can you see how close it is? 9,995 mega ohm, and R3 was 10 mega ohm because this value is very large. Alright. Okay, that concludes then the common gate amplifier, also with the cascade amplifier that's been used in a multi-stage arrangement. Okay, so now for these three configurations of amplifiers, you have to finish the basic problems up to number 31. Just to make sure that you're not bored during the holiday.